start with a word of prayer. Dear Father, we just thank you for this afternoon. I just pray you'd help us use this time wisely to glorify you, what we do, Lord. In your name I pray. Amen. So last time we were messing around with I don't know what it was, section point 2, some kind of set theory problem, and we were trying to do it without chasing points, and we got a little bit lost in the algebra. But if you look at the YouTube channel, Alan, not here laying, made a comment, which, but anyway, I don't care if he doesn't come here. If he makes comments like this, it's awesome. And his comment actually shows how to do it without points. So if you look at the YouTube channel, it's there. And we're not far from it either. There was just I don't know what we drifted off course somehow. I'm not sure what exactly kept us from seeing that. Yes, the Tuesday, but in any event. So, do you guys have questions? Unfortunately, I don't have my. I have my book. I should probably get out my computer so I can see. So the rules in here. I'm happy to clarify language and mission questions, but I won't work mission questions. But I'm happy to work or attempt to work training exercises for the most part. Yeah?
What's the difference exactly?
Well, you should look. Aren't you the president?
Hey, I got things to do. All right, you're on the list. But since it's not due till Friday, currently you are third on the list.
Uh-huh. So what you're telling me is I should move the due date up.
I don't like where this is going, mainly because you can do that. It's the first week. A lot of people are like, welcome back to school. Come to all of our meetings. So to go to all their meetings, they won't have to get
Stupid meetings. Stupid meetings. Let's see here.
One right after this.
All right. So you guys got questions? I don't know if I've got answers, but you can ask them. Mm-hmm.
So in question problem number 2, I just like some of the language clarified. There are a lot of symbols, and some of those symbols I've seen before. Some of them are being used in a slightly different way.
Number 1.
Problem number 2, it's point 4, number 9.
So, it's looking at a set A, mapping alpha, another set B, the natural map phi to the quotient set A, and then there's some kind of section over here called I don't know if he calls it a section or not, but so you're given, what are you given? Is equivalence relation, right? On A, phi of A is what?
It's a natural map.
Right, but what is it? What is it?
An element of A equivalence.
Right, it gives us the equivalence class of A. Now, I haven't said quite, this is not any equivalence relation. This is a very specific equivalence relation. Right, this is the what? This is the kernel equivalence, as he calls it, of the map alpha, right? So what was the definition of that? We said that x1 is equivalent to x2 if and only if what?
I think it's f of x1 is equal to f of x2.
Right. In this case, it's alpha, but yeah.
Yes, alpha.
But your heart's in the right place. So it's cool. So that's the equivalence that we're dealing with here.
Is it alpha or phi?
It's alpha.
alpha.
But that goes to 15 times
Hmm?
No, I was just looking at the chart. I'm thinking if it's going from A to the A equivalent set, that's what, and then now I'm looking at X1 is equivalent to X2. I can put those in the same thing in my head.
Yeah, I sometimes, well, I would think of A like this, and I think of the equivalence classes like that. You know, I don't know. But then these equivalence class, these subsets of A become points in their own right down here. You know, I mean, we think of them as points in the quotient set. It's a set of sets. So the elements are subsets in A sub bar bar bar. So what does he tell? He says define. What's he say? Define sigma. Sigma is going to be going from here to here, right? So he says define sigma of A equal to what? I'll tell you, forget about A. Let's use X for a second here. What's he say it's defined to be?
It's defined to be the equivalence generated on class of X equal to alpha of A, correct? Is that interpreting that properly? Or of X in this case?
Well, he says that sigma of the, oh, you're just telling me what this means.
Yes.
Yeah, but he tells us that that's equal to alpha of X, right?
Yes.
Yeah. So what's your question? I mean,
Honestly, that helps out a lot. I just wanted to sort of make sure that I was understanding all of the terminology properly. When I was saying, oh, this symbol means this symbol means that, I was interpreting what the author was trying to get through to me properly.
right. I mean, this is built off his example 4 on page 18, where he introduces the kernel equivalence. But I mean, I can talk a little bit more. So one of the things you're supposed to show is that this mapping, this sigma mapping is well defined, right? In other words, you should show that this formula is independent of the represented. I mean, we're using the generator of the equivalence relation to define the action of the sigma map, right? So one of the things we should show is that if we have x equal to, say, x prime, then we should also get that sigma of x, right, is equal to sigma of x prime. Because if that's not the case, then sigma is not single valued, right? So you got to check on that. So he says, show that sigma is well defined and 1-to-1. And it's onto if alpha is onto, yeah. So I can't really, if I say much more about those, I'll end up solving them. There's not much. It's really just chasing definitions there. But yeah. Any other questions? So do any of you guys care about the well ordering principal argument for a division algorithm? Mm-hmm. Like, is it helpful to you if I go through the proof on page 32? No is an acceptable answer. I'm just asking.
I'm pretty sure I've seen that proof before.
Okay, that's what I kind of think is you guys have seen that. No, it's the proof by contradiction that shows you that the least member exists and it has to be the remainder, I think, if I remember right. Yeah. Pragmatically, the Euclidean algorithm actually gives you an alternative constructive proof, right? Because you keep doing successive division, the remainder at each step gets smaller, but it's a positive thing that's getting smaller. So since it's a finite number, that recursion has to truncate at finite number of steps. And so the recursion ends, and that proves that there exists, because of the back substitution, there has to exist a GCD. I mean, the Euclidean algorithm gives you an alternative proof, which is constructive as compared to that well-ordering principal argument on 34. So you guys have a homework question you want to ask me about? Or? Yep.
If I could you explain what permutations are? Because because I've heard them explained a couple times in their
Ooh.
classes, but that's just something that I've never really been able to wrap my head around, and I know that's what we're going to be going into next, and I don't know
Yeah.
everyone else, but it'd be helpful if I had a little leg up, so I could try to. I don't know why I've never been able to really cement what they are.
Well, generally speaking, permutations, I think I said this the other day, but the permutations on a set S, that's just equal to, sigma, or whatever you want to call them, mappings from S to S, excuse me, such that sigma is bijection. So they're one-to-one and onto mappings from a set onto itself. Those are permutations of S. You can think of them sort of as they're just taking the elements of S and scrambling them, right? And then usually we let S equal to 1, 2, 3, n, in which case the permutations, let me call this thing the natural numbers up to number n. So like perm on the natural numbers up to n, that we usually denote by S sub n. This is, for technical reasons, called the symmetric group on n symbols. But we'll get there in terms of group, but they're just bijective maps on a set. That's all a permutation is. So I'm not sure how far we'll get Friday on that. We learn a bunch of neat technical sneaky stuff about the cycle notation for permutations that gives us ways of calculating with them that's very efficient and neat. But at the base of things, they're just bijections on a set. Yeah. Yeah. Let's see here. Let me.
Yeah, I have a problem.
Okay.
Okay, number 6 on the test training. It's 1.2, number 17.
1.2, number 7. That sounds like the kind of problem I should be working right now. That's perfect. Let's see here. Yes, thank you. That is a helpful suggestion here. So number 7, section 1.2. Number 17, did you say?
17.
Yes, okay. So this one says if the greatest common divisor of m and n is 1, right? And the greatest common divisor of, where were we? Yeah, k and n is 1, then the greatest common divisor of mk and n is also 1. Let's put this into words. If m and n are relatively prime, right? And if k and n are relatively prime, then the product of m and k is also relatively prime to n. That is not the proof. That is a restatement of the problem. That will get you 0 points. And I will write you this. And then I will laugh at you. So, I'll give you 1 point? Oh, Andrew knows me too well. Yeah, I'll give Andrew 1 point. Everybody else I'm going to give 2. But, sorry. I think we can use Bazou's theorem. I mean, when I see that, once you have a hammer, everything looks like a nail. And to me, that's what Bazou's theorem is. I mean, so there exists x and y, and let's get to it. Just get it over with. A and b in the integers, such that what?
1 equals
Right.
x n
Okay.
plus y n.
All right.
And 1 equals a k plus b. Or, yeah, b.
All right. Oh, wait a minute. You guys are asking me this, which means it's not that easy. Or wait a minute. Maybe you're just starting, so it could still be easy. Okay, all right. There's still hope for me. certain students, like they come and ask you a question. It's bad. It's bad. If they're asking you, it's bad. Let's see here.
I tried setting them equal to each other, but that's all I've tried so far, and it didn't give me any.
Just set them
'Cause
equal.
I was like, maybe.
Let's see here. Let's see here. Let's see here. So I'm gonna take this one. I'm gonna try something here. I think this might be helpful. And then that's equal to what? That's equal to xm times ak plus bn. Because it's 1, right? So we can multiply by 1. And 1 is, this is 1. But then distribute. We have axmk, right, plus, let me do the math here, mxb plus y times n since ax and mxb plus y are in Z, this shows the greatest common divisor of mk, and n is also 1. By what? By theorem. Which theorem am I using here? It's not one of those theorems that has a name, it just has a number, you know? So, I mean, I'm only
Where are we using the theorem?
in,
Or the theorem is the problem?
we are using theorem 4 from section 1.2 in my conclusion. See, because what's my logic? My logic is I've just produced 1 as an integer linear combination of mk and n, right? There exist integers, ax and mx plus by, such that those weights times mk and n give me back 1. Theorem 4 says if you can do that, the greatest common divisor of those two numbers is 1. So, I could totally imagine there being a book out there which takes that as the definition, right? Like m and n are relatively prime if and only if this happens, you know? I mean, if only if there's an integer linear combination of the numbers that gives you 1. Oh, wait, there it is. Next. Yeah.
Bit of a random tangent. What is that symbol for the 1.2? I see it on the missions and up above. What does that symbol signify? Yes, that
Section.
section. Okay.
Uh-huh.
It's a fancy. Yes.
Yeah.
All right.
I believe it is \s or something like that in LaTeX. I don't know. Although I may have the wrong slash. I don't know. Let's see here. Let me look at a problem from one. Let's find a problem in 1.3 to work. How about that? What's a problem in 1.3 I've assigned? Let's work one. In the training, please.
1.3. You have a view. 21 is the first one.
21.
If you want to do that.
Okay. I'd
Make
really
you do
no. Let's.
later.
Can we find a one that's not quite so?
I have,
How about 25? Did I do anything in 25?
yeah, you did.
So which one? Which one? 25? Oh, I did. AEF, is that in training or mission? Okay. Okay. I don't know, why am I even asking? So you're 1.3 numbered, what did we say, 25? 25A. I should probably, 3 bar X plus 2 bar Y equals to 1 bar. And 5 bar X plus Y equals to 1 bar. This is happening in Z11. We're trying to solve this 2 equations and 2 unknowns. 1 bar. Yeah. There's no T. I don't know. I mean, I haven't really. I read this section a while ago, so I'm not going to tell you how Nicholson says to do it. I'm just going to do it. Okay. Okay. So basically, I just got to make them look the same. So if I take the second equation and I multiply by 2, you got to be careful when you do that. You can't multiply an equation by something that doesn't have an inverse. If you do that, you can get into trouble. But certainly 2 has an inverse in Z11. What's 2? 2 times what equals to 1 in 11? What's the multiplicative inverse of 2 in Z mod 11 is my question. 6. Very good. Because 2 times 6 is 12, which is 1 in Z11, right? So if we multiply the second equation by 2, we get 10 bar X plus 2 bar Y equals to 2 bar, right? Times 2. Oh, I'm sorry, I hate that notation. Multiply by, I do not. And I should show you guys the problem that Daniel had to solve in his arithmetic the other day. It's about ratios, and it's just maddening. I need to bring it. Okay, anyway, so the reason I did that was so that these match. Then I can basically subtract equations, you know, and which is just another way of saying, so that's 7 bar X is equal to 2 bar minus 1 bar, but that's 2 minus 1 bar, which of course is 1 bar, right? So whatever X is, it has to be the multiplicative inverse of 7. What's the multiplicative inverse of 7 in Z mod 11? So I have to solve 7 bar X equals to 1 bar. In other words, what's the inverse of 7? What times? 8 times. Oh, very good, yeah. So 7 bar times 8 bar is 56 bar, otherwise known as 55 plus 1 bar, also known as 1 bar, right? Yeah. Because 5 times 11 is 55, yeah. So very good. So that means that X is equal to 8 bar. And once you know that, you should be able to go back to one of the original equations to figure out what Y is, right? So like Y is equal to 1 bar minus 5X bar, right? Which is 1 bar minus 5. I put a bar on the X. I'm an idiot. I'm really getting tired of these bars. Very tired. But I will suffer. Yes. At the end of this section, he gives a disclaimer. Past this point in the book, I will be removing the bars. So I am looking forward to that moment in our development. But anyway, so that is minus 39 bar, right? Which is also known as what? Add. add 44 to it, right?
5 bar?
It's 5 bar, right, yeah. So there we go, that's our solution. X equals to 8 bar, Y equals to 5 bar. At this point, we can go back and check, right? Does it make, we should always check, right? So like, I get 24 plus, 24 plus 10 is 34. 34 is 1. Mod 11, right? Good. First equation checks. Second one, 5 times 8, 40. 40 plus 5, 45 is 1. Checks. Okay. That's one way you could solve it. There are other ways. Want to see another way? Let me show you another way.
Didn't you have another notation besides the bar to know, like a number that was in 11?
Well, I have used the notation x bar, which is our from chapter 0 equivalence class notation, right? It is also equal to x plus nz mod n. These are the same set. And after this, I mean, after this section, we just pretty much use x here. So, but we're not, I mean, if you're working with like, some people in lower level math, they would actually put bars on the x's too, because they're variables in the mod thing or something. But another way you could do this, which would be fun, would be to rewrite it as a matrix equation. I think you're right. I'm pretty sure I did. X, Y. So the inverse matrix will exist in the same formula works, but you got to be, what do you mean about it? This is 3 bar times 1 bar minus 5 bar times 2 bar, multiplicative inverse of that, whatever that is. And then, the drill, we flip the diagonals. We put minuses on the off diagonals. So many bars. Painful. Whatever that works out to. I mean, this is actually a useful calculation for us to go through. Let's see here, 3 minus 10 is minus 7. What's minus 7? Minus 7 is 4. So we're looking for 4 inverse. And here we've got 1. We've got ourselves, we can leave the minus 2, minus 5, 3. I forget, you know what? I just lost the bars. I'm sorry. I'm done. I'm out. I can't take it. It's enough. I don't get paid enough. So what's 4 inverse? It's, I don't know, something.
Now with the 4s, usually have a bar as well. You don't have to put it. I just I'm not assuming negative numbers in modular division. So when you have negative 7, you change that to a 4. I get why it's a 4.
Oh, okay.
But would that 4 only have a bar?
Yeah.
You don't have to put it. It's fine.
Okay.
Just making sure.
Okay.
Don't do it.
I'm not. So what is the inverse of 4 mod 11? Three? 3 times 4 is what? 12.
I skipped.
AKA, you skipped 3?
I was like 416.
So that's 3. So I multiply through, I get 3 minus 6 minus 15, 9, which we can reduce to what? That's 3 minus 6 minus 4, I suppose, 9. And then, yeah, and so then we just, this is basically m times vector equals to that. So the vector is m inverse times 1, 1, 1. Lost my bars. And of course that is 3 minus 6 minus 4, 9. times 1, 1, which we can multiply, and we get 3 minus 6 minus 4 plus 9, which is minus 3 and 5, which of course is congruent to 8, 5, yeah, which is what we got. So most of linear algebra still works over Z, like Z11, because Z11 is what's called a field. Every non-zero thing has a multiplicative inverse, so the usual calculations will still make sense. Now, if we're in something like Z6 or something that's not a prime, Z mod not a prime, it's more complicated. We have to be wary. We have to watch out for those zero divisors, and there's more to it. But anyway, let me. How about this? What if we wanted to solve? I guess one thing I should talk about a little bit is, what if you wanted to find if 100, what is 100 inverse mod 101? I mean, 101 is a prime, so results that I'll try to discuss carefully tomorrow prove that every non-zero thing has a multiplicative inverse. How do you find it, though? Besides just guessing numbers. Guessing numbers is the right approach for mod 11. You only got 10 choices, right? But this, we need some better way, right? So, see, I'm trying to remember how to do this. We do 101. Yeah, we got to use the exactly Euclidean algorithm is the way to go. So, how do we do that?
You talking about the greatest common divisor again, or something else?
Don't you like?
Yeah, that'll work. Perfect. Let's calculate the greatest common divisor of 100 and 101. Why would that help us? Because this will be equal to 1, right?
Right.
But that 1 will also be equal to m times 100 plus what? I'm sorry, x times 100 plus y times 101. Sorry, it's been a long day, and my brain got burnt there for a second. But this is actually, that's spot on. That's exactly what you want to do, because by Bezout's theorem, there exists as x and y, right? But what this means then is 1 is congruent, right, mod 101 to what? X times 100, right? AKA, whatever that x is equal to 100 inverse in Z101. Right? So yeah, that we want to do the Euclidean algorithm on that. How do we do that?
100 equals. No, 101
Yeah,
equals.
101 plus 1.
100 times 1 plus 1, right?
Right. Bring over that 100.
100 equals.
100 times 1. I don't like
Yeah.
this.
1 times 100.
Plus 0. Look at that. That's
There
1.
we go.
All right.
There is no greatest common divisor.
Oh, so there you, I mean, so basically we just go back up to the initial one, and and we find out what
So it is just 1.
1 is equal to 101 minus 1 times 100, right?
I knew it.
So it's negative 1.
It's negative 1, right? So 100 inverse equals minus 1. Also known as?
Oh, 90. No.
I should add 101, right?
Yeah.
Oh,
What?
100.
Oh, I'm saying.
whoa. My mind is blown. No. So apparently 100 is its own inverse, mod 101.
That's pretty cool.
wonder if this works for similar things, huh? What would be an analogous question with different numbers? Like the same sort of numbers, but what if we tried, what's 20, well, how about does that work? Well, I mean, I wonder if it matters that 101 is prime. We could try like, what, we could try like 25 inverse mod 26 and see how that goes. I'm curious. So like 100 is 10 squared, right? And then one more. Oh, we proved last class, if I could remember 3 minutes ago, what did we prove about successive integers?
Oh, no, it's always relative. I was saying, we put the algorithm.
They're relatively prime, right?
So it's always going to be what?
So if you're working in Zn, it turns out the numbers in Zn which are invertible are those which are relatively prime to n. So like in Z6, 2 is not invertible, 3 is not invertible, 4 is not invertible, just 1 and 5. Because are those the only ones that are relatively prime to 6, right? 2, 3, and 4 all share common prime factors with 6. 0 is never invertible, so you can forget about that one.
So if you're working in like a Z mod n, would any n, or would any factor of n be non-invertible?
Yes. Right. Because if you have a factorization of n, whatever is the sort of cofactor to that, when they multiply together, they give you n, which is 0, which means that they're a zero divisor. And we can prove that if something's a zero divisor, it can't be a unit. A zero divisor is like a times b equals to 0, with a not equal to 0 and b not equal to 0. Suppose A inverse also existed with, A inverse times A equals to 1. We can think of these as being modular integers for our discussion, since we don't know about other things too much yet. But so if you multiply this by A inverse AB, what do you get? So this is 0, and this is 1 times b, which, as you just said, b. Oh no, but it's not equal to 0. Ah! Contradiction. No can do. It's either, you can't have a zero divisor which is also a unit. These are separate categories. For modular, for Z mod n, everything is either 0, a unit, or a zero divisor. Those are the 3 categories. For a general ring, there are other possibilities. But anyway. Okay, so how about this one? Let's go back to here. I'm pretty sure we can do what? 26 minus 1 equals 25, right? So like, what's that say about, does it say anything? I don't know. Or is that not useful? Oh, so that's it. What does that say? I can't do math. I'm sorry, guys. My brain is broken. What should I write? What's the inverse of 25 mod 26? Is it 25 again?
Yeah.
How did you show it?
On the table.
Actually on the table. He just wrote it on the table. Okay. A little bit different, but I guess I'll allow it. I'm trying to...
Same way Euclidean algorithm show that the greatest common divisor is 1.
Okay, so it's the same silly 26 is equal to 25 times 1 plus 1, and then you're like, okay, so 25 is 25 times 1 plus 0, and you're like, okay, well, back up here, bingo, 1 is equal to 26 minus 1 times 25, right? Or plus minus 1 times 25, if you want to look at it that way, fine. And then mod 26, we get 1 is congruent to minus 1 times 25. Right. And then when we add 26, so minus 1 is congruent to 20. It's congruent to 25, yeah. Mod 26, yeah. So 25 inverse is 25 again. Kind of neat, right? There's something more general we could say here, isn't there?
The number, right, like n minus 1's inverse is always itself.
Yeah, like when is it, what does it mean for, what does this mean if we have like x inverse is equal to x mod n, you know?
Did you say x equals n minus 1?
Let's see here, that mean, and
That's what you're saying, like if it's mod.
oh, right. I actually was stepping away from the specific relation between, I mean, yeah. Here there's a specific relation between the n and the x. I was just I'm just taking a step back and just saying, for n, you know, what would that look like? Well, that would be, we'd have what x inverse is equal to xx, right? So this would be solutions to x squared equals to 1 mod n, right? In other words, which numbers squares are congruent to 1 modulo n? N minus 1? X equals to n minus 1. Is that always a solution? Has x squared equals to n minus 1 squared, which is n squared minus 2n plus 1. Yeah, that is congruent, of course, to 1. So yeah, n minus 1 is always, apparently, n minus 1 is going to be its own inverse mod n. Cool. Whether n is prime or not, you know, like, whoa, that seems wrong.
Wait, hold on. At the very end, when you get to n squared minus 2 equals 1, it's equal to 1.
Because n is 0 mod n.
Oh, there we go. I was gonna say, how do we know? Oh, that's true.
So one number less than the modulus always has to be invertible in its own
26 was
inverse. Is that right? Let's try it out.
That looks right. Sounds right.
So like suppose we're working in Z10. I'm saying that 1 less than 10 is 9, right? And 9 times 9 is what? 81, which is of course 1 mod 10. So 9 inverse is 9. Cool. What if we...
always done perfect squares, though.
Oh, let's try something uglier, like 153.
Oh, 25. You're right.
So allegedly, if we trust our math, 152 inverse is 152. Thank you. Thank you for bringing a calculator. I very much appreciate that at the moment. So what is 152 squared?
You got 23,104.
22,000, what?
23,000.
23,104, okay. And that is congruent to what? Divide by 153, what do you get?
851. That's the decimals.
What are the decimals? 100, so divided by 153 equals 100, what did you say it was?
It was 151.
151 point
006.
006. All right, how about this? Instead of that, take 23,104 and subtract 151 times 153. What do you get? 1. That's right. Which shows you that 152 squared is congruent to 1. Which means that, indeed, 152 inverse is 152. But isn't it amazing how much easier it is to prove that, like, one of the solutions to this congruence is just the modulus minus 1 for arbitrary n greater than or equal to 2? It's crazy how much easier it is to see that that works than it is to actually check it for specific examples. Huh. Man. I feel like I should have already known this, and like it should be hardwired into my brain, because this saves me work, you know? This is not something that, I don't know. And if you had number theory, you already know so many things if you were paying attention, right? But, I mean, the problem of solving a quadratic equation, quadratic congruence, this is a difficult problem in general, right? This leads us to study those what? Reciprocity? Is it the reciprocity? I can't say words. Gauss's reciprocity? Yeah. Thank you. I shouldn't even try to help you guys this time of day. I don't know what's wrong with me. My help is, I should. All right. Do you guys have other questions? Ooh, I like number 15. Did I assign it in the mission?
1.315?
Yeah. This is a great...
Right, the mission. No, you didn't.
All right. Hey, look at this. Now he's using bars for the variables. Isn't that cute? Did you use Bob Saget as an expletive? I think he would be honored. Bob Saget's not ABC humor is not really suitable for the shows that made him famous. Let's see here. A times A plus 1 times A plus 2. We're supposed to show that this is an identity in Z6.
That's zero's identity.
In other words, this for all A in Z6.
But they all equal zero.
If you think about it for a second, it's obvious why this is true. I mean, like, but how do you prove an identity in Z6?
Cases, they're fine.
Yeah, exactly. You just do cases, pretty much. I mean, it's so there are how many choices?
Do you include zero?
Yeah, there's right. So you can do it that way, you know, 0 times 1 times 2, 0. 1 times 2 times 3, 6, otherwise known as 0. 2 times 3 times 4, which is 24, which is 0. You'll forgive me for not using the bars. 4 times, oh, I'm sorry, I can't do math. 3 times 4 times 5 is 60, which is 0. And, you know, if you're lazier, you could make arguments like, well, there are ways to be lazier here, but let me not be lazy. I'll just be completely unclever and just, oh, 6, but 6 is what? 0. And 5 times 0 times 1, yeah, okay. Why do I have a 0? 0, oh, okay. I think that's all the, that's A equals to 0, 1, you know. Now, I think you start to see here if you know, this one's not too bad, so why not just write it and say, okay, there you go. That's everything. As you can see, it's 0 in each case. It's an identity. But if you start looking at it, there's probably, if you had like a larger modulus, you could sort of divide and conquer. There's some kind of argument you could make to say that some of these cases are actually the same case, right? Like, I'm trying to see here. Yeah, anything with a 0, right. You could look at all the cases where you got 0 and like treat those at once. If any of these are, what does it take for one of the product of these three things to be 0? How would that happen? Or you could do something like look at A even versus A odd or something. There are other games you could play, but yeah, that was kind of it. Let's see here.
Was that mission problem?
Was it? No, I don't. I hope not. That'd be boring to grade.
I'll send it through. Like these.
So, how about number 20? Did I assign 21 part A in the training? What did you say?
What's in the training?
Let's talk about that one. We'll end with that. I'm hoping to talk about the casting out the nines tomorrow. Like I'd like to actually derive that carefully. You guys don't know, casting out the nines? You can tell if a number is divisible by 9 by adding the numbers together.
Oh, yeah.
If it's a multiple of 9, it's divisible by 9. So 21a in section 1.3 is to show that 3 divides n if and only if 3 divides d0 plus d1 plus da 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 plus dk. What are d0 and d1? Here n is equal to, dk minus 1 da 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 d. You gotta understand what this notation means, right? We're trying to denote the decimal representation of n, right? What does the decimal representation of n actually mean? In terms of an honest to goodness formula, I'll start with the lowest thing. The units place is just d0, right? What's that d1 here actually mean? Plus d1 times 10, right? Plus d2 times 10 squared. dk times 10 to the k. This is the decimal representation of a number.
So you're not multiplying dk and dk minus 1.
No.
It's different places.
This is, it's the decimal representation of a number. So so let's see here. Let me just do one of the directions here. Let's do this direction. Let's suppose that 3 divides d0 plus d1 plus dk. Meaning what? I don't know if that really helps. Let me just say 3 divides the sum of the digits, okay? That's a suppose.
But that's not like the
Suppose.
digit times 10.
Suppose. So, observe. I don't have a symbol for observe, weirdly enough, but n is equal to d0. I'll just rewrite what I wrote again. 10 times d1 plus 10 squared times d2, 10 to the k times dk, right? What is 10? 10 is equal to, let's see here. Mod 3. What's 10 congruent to mod 3, I should say? 1. Oh. So what's 10 squared congruent to mod 3? 1 squared. also known as 1. I think you see where this is going. 10 to the j, whatever j is, congruent to 1 mod 3. So this implies that n is congruent to d0 plus d1 plus d2 plus da-da-da plus dk mod 3 because of this. So since I know that every power of 10 is congruent to 1, then that means that n is congruent to the sum of the digits, mod 3. But what does that mean?
That 3 divides them.
Right. Well, we're given, I'm sorry, we're given that 3, I'm sorry, my brain is just gone now. 3 divides this, right? That means that the sum of the digits mod 3 is congruent to 0 because it's a multiple of 3. So by assumption, this is congruent to 0, which means n is congruent to 0 mod 3, which means that n is a multiple of 3. In other words, 3 divides n.
Does that only work with tens?
Oh yeah, if you use other bases, there are other rules. I put those on tests. But so like 157, is it divisible by 3? 1 plus 5 is 6, plus 7 is 13. Nope, not divisible by 3. Right. Is 1,897 divisible by 3? I need to come up with one that's actually divisible by 3 so we can leave here. Make a 7. Did I get it now? 8.
Yeah.
Yeah, 8 I hopeful it's 3 minus 1,800. It's 3 less than 1,800. So the fact that it's divisible by 3 is evident to anybody who has any kind of number sense whatsoever, right? But also by this fantastic rule of 3s, right? So the rule of 9s is more impressive. There's also a rule of 11, but then you have to like do plus minus the digits because like 11 is congruent to minus. So mod 11, 10 is congruent to minus 1 mod 11. So if you take the alternating sum of the digits, that tells you something about divisibility with respect to 11. 8 is 10 is congruent to minus 2 mod 8. So if you wanted to look at divisibility by 8, you got to look at like the alternating multiplied by 2 weighted sum of the digits. Like there's tricks. They become less and less useful the further you get away from 9. Like right in the middle, they're almost completely useless, like 6. The 6 and 7, whatever. 5, divisibility by 5, we can just see, right? You know it when you see it. It's not hard. Anyway. All right, I think I said enough. I'll see you tomorrow. I'm sure I will not get very far into permutations tomorrow because, I think I should. That's my question is, have you guys actually seen modular arithmetic pretty much before? So I should probably just go on. It would make more sense for me to go on to permutations and spend more time there, right?
Look, I've seen it once before.
Yeah.
I think it's nifty though, so I love spending time on it.
I mean, what I'm trying to say is I probably should just say with authority what we learn in the modular arithmetic section and just go on to permutations for the bulk of the lecture. That might be better for everybody involved. I just don't know what you guys know from previous courses because I've taught number theory once. I've never taught Math 200 here since like 2009, so I don't know what's happening in earlier courses in terms of what you guys see. And I don't really get a lot of feedback on the fly. Like I look at you guys, I'm like, did you see this before? And you guys are like, I'll never tell.